Okay, so in this video, we are going to go through parametric equations and Cartesian equations. And for some reason, I had that thing there, but it's just there it is. Okay, so what we're going to do is first of all start with a few examples and give you a few tips. And I think that all of these should go in your bound reference. Now, let's have a look at this one. This is what we just sketched on the CAS calculator. Now, just so you know, and just so we put on the video, this is a sketch of what it looks like. And in order to do it, you go to the graph screen and we'll go to a new graph. And what we're going to do is going to go menu, graph entry, edit, and we're going to go parametric. As you've seen there, so we can put it in and as we've just sort of shown you, this is a circle. But why is it a circle? Well, let me just talk about it. What do you notice about the coefficients of sine theta and cos theta? They're the same. So the moment you see that they're the same, you know it's going to be a circle. Okay? Just that's the trick. Okay? So they're the same coefficient. So therefore, that's going to be a circle. Okay. Of course, we've got to rearrange it. So what we're going to do is we know that cos theta and sine theta, there's a relationship between the two, and that is that if I get x minus 2 and I divide it by 3, that's equal to cos theta. This is how you should do this, because a lot of the time you have to show that. So that would be the first step, showing that cos theta is equal to this, and y minus 1 over 3 is also equal to sine theta. Now, of course, what we need to do, therefore, since we know that sine squared theta plus cos squared theta is equal to 1, you could just literally, unless it was a show that question would be different, we can say x minus 2 squared and 3 squared is 9 plus y minus 1 squared over 9 is equal to 1. Look at that. So what we have, as we have discussed, we have a circle. We have a center at what? 2, 1, and we have a radius of 3. Okay, and that's exactly what we've shown you in this CAS calculator. If we do it one more time, and that is x is equal to 2 plus 3. You can type in cos, or you can just go to trig and cos. It does actually allow you to type it in. 2 cos of t. Be careful, t. Go putting in theta, the calculator is going to go, oh, I don't know what's going on. Y is equal to 1 plus 3. Oops. What have I done there? See what I mean by like, for example, if you're in exam 2 here, can you see there that I've just made a mistake? It's actually taken me longer to put it in the calculator than it has to actually explain it to you. So that's why you've really got to pick your battles. And even if this was an exam 2, I would expect you to be able to do it faster. So let's try it again. Let's try it again without this stupid pen. Parametric, and I'm going to do 1. It's easier if I can type. 2 plus 3, 2 plus 3 cos. It's actually really hard to do with this pen, ladies and gentlemen. Okay, and we'll go to, what's going on? Usually you could just press enter or why? There we go. Okay, 1 plus 3 trig sine of t. And that will sketch, you can see the domain is from 0 to 6.28, which is 2 pi. And as you can see, that is a circle centered, what is it, 2, 1, radius 3. Okay, and you can do that for any of them. Alrighty. Are there any questions so far about what we've been through? Now, what do you notice here about the coefficients, ladies and gentlemen? They are different. So this is not a circle. Does anyone want to give me an example of what it could be, given that we stretch a circle out in a certain direction? What do we call that? It's an ellipse. When you see these and you have sine and cos, but the coefficients are different, it's going to be an ellipse. When you see second tan, probably a fair chance you'll see a hyperbola. And these are the things that would need to go in your bound reference so you can study them for the rest of the year rather than simply forget it in a few weeks because you don't practice these skills for months again. Okay, so what we're going to do is I'm going to very quickly do this. I'm going to say that x minus 3 over 3 is equal to sine of t. This time our parameter is t, not theta. And we've got y minus 2. I'm going to do over minus 2 is equal to cos of t. Now, the reason I do that, don't worry too much about that minus 2, because when I square it, it's going to be positive. So what we're going to say is, therefore, x minus 3 squared over 9 plus y minus 2 squared over negative 2 squared, which is positive 4, that's equal to 1. Just like the same thing we've done before. But therefore, because these things are different, this is not a circle. This is an ellipse. This is an ellipse. And what I guess you could say is you could have, it has a center at 3, 2. We can say that you've got a horizontal semi-axis of what? Is it 9 or at 3? And a vertical semi-axis of 2. And we could literally just sketch that without even having a calculator. Well, I've got the coordinates 3, 2, 3, 2. So here's my center here. Let's say that's 3, 2. But vertically, we're going 2 down there. So it's going to look something like that. Yeah. That's okay. Shoot. Okay, now you can see there that we could draw this quite easily, couldn't we? What would be the y-intercept? Horizontal semi-axis is 3, so doesn't it go over here? Doesn't it go over here? Is that sort of what our ellipse looks like roughly? With it being a really bad drawing of an ellipse? Yeah? So we could even find what the x and y-intercepts are because of course they're on the axis itself. All right, so what you need to identify is if the coefficients are different, but it's a sine and cos, it's going to be an ellipse. And if it's not an ellipse, you've made a mistake. Okay. All right. Now, what do you notice here? We've got a second of tan. So we've been through a circle. We've been through an ellipse. What do you think this is going to be? It's going to be a hyperbola. And of course, we've been shown that. So this is an example of a show that question. And look, the thing is, the problem with this is that every student in the cohort should get 2 marks for this, but they don't because they get slack and lazy. I'm going to show you how to get 2 marks every time. Okay, what we're going to do is now, just so you know, this is actually from vector calculus, but in actual fact, it's really quite a straightforward thing. The I component is the x, and the j component is the y. So we're going to start with that. X is equal to 4 sec of t. And we're going to write everything out. Y is equal to 2 tan of t. Now what we're going to do is I'm going to get sec t and tan t by itself. So what we're going to do is we're going to divide by 4, and we've got sec t. Do not skip any steps because it is a show that question. Okay, if you go from there to there, if you sort of go from this step to that step, you will get 0 marks. Okay, if you make it a fair way, you might get 1 mark, but unlikely. It needs to be very clear. So now, as you can see, we've got that. Now what we're going to do is we're going to square both sides. We can say, therefore, x squared on 16 is equal to sec t squared. Be careful, use the correct notation that they've given you. And don't start changing t's to thetas. All right, and that's equal to tan squared t. Okay, so what we can say is we can say since sec squared t minus tan squared t is equal to 1, therefore x squared on 16 minus y squared on 4 is equal to 1. Can you see there that you've shown what tan squared t and sec squared t? You've talked about the identity, and of course there it is. We can sketch it. Okay. Now, in actual fact, this is a point that I wanted to. This is probably the most tricky part about these parametric equations. Yes, there's going to be 3 types for the most part. There's actually going to be more types because ellipses, hyperbolas, and circles you'll mostly see. But I'm going to give you an example where it's an exam 2, and it's something that looks like an infinity symbol. Okay, because we've got a use of a calculator. Okay, it's not always going to be that, but whenever you see second tan, hyperbola. Cos and sine, it's either going to be a circle or an ellipse, depending on the coefficients. Okie dokie. Now, so we could sketch this, but I just want you to take note. Take note of the domain, because in actual fact, in the 2013 exam 1, part B is actually sketching this. But when you sketch it, you need to be careful. The particle starts at time 0 and stops at pi on 2. A lot of the time with a circle, we know if we had the domain of 0 to 2 pi, then we know that it's just going to be a full circle. Okay, the period of that circle would be 2 pi. But this is where it gets a little bit tricky. So find the Cartesian equation of the parametric equations, sec t and tan t. First of all, let's have a look. Sec t, tan t, what does it mean? What's the shape going to be? A hyperbola, absolutely. So what we're going to do, we don't have to show anything. So what we're going to do is we're going to just go straight to x over 3 is equal to sec t, and y over 4 is equal to tan t. We know that it's a hyperbola straight away. And what we're going to do is we're going to say that x squared on 9 is equal to sec squared t. I'll show you exactly. Y squared on 16 is equal to tan squared t. So what we can say is, therefore, the Cartesian equation is x squared on 9 minus y squared on 16 is equal to 1. That's our Cartesian equation. We've gone from parametric. However, look at this. Now, let's just sketch. We know what x squared on 9 minus y squared on 16 hopefully looks like. We can go, the thing is that what's the center of this hyperbola? Where's the center? Has it been moved to the left or to the right? No, so the center is the origin. Okay, so without even thinking about it, sketching it in a case, we're going to have some graph, and forgive me for, that's a gradient of 1. Okay, but let's just say we're going to have some hyperbola. Is it going to be an east-west hyperbola or a north-south? It's going to be an east-west, and forgive me, it's going to look something like this. I'm just talking about the shape here, all right? And of course, that's going to look much better than that. Now, what you need to do though is we need to consider what the domain is. So what we're going to do is we need to check the endpoints. And that's the tricky part. It gets a lot of students that just do not do this very well. So it starts at t equals pi on 2, not 0. So at t is equal to pi on 2, let's check both the x and the y. There is no point throwing this into here. Okay, that's the Cartesian, that's the particle. But that particle is going to, we're going to have, this is sort of, this x, the I component, or this x is sort of going to represent sort of the domain, this y is sort of going to represent the range. Okay, so what we're going to do is at t equals pi on 2, we're going to find out what x is equal to. So we can say that x is equal to 3 sec of t. Now 3 sec, that's 1 on cos, isn't it? 3 cos of pi on 2. What's now remember, does it actually go to pi on 2? No, it doesn't. But that would be sort of undefined, wouldn't it? Okay. So why don't we check somewhere in the middle? Okay. What about if we go at t is equal to pi? Now, as t is equal to pi, now this is a particle which starts somewhere. Okay, you're probably better off just thinking about another point, like you could pick yeah, so let's see where pi is. At t equals pi, x is equal to 3 over cos of pi. Cos of pi. Now, what's that? Cos of pi is -1, isn't it? So that's going to be -3. Now, at t equals pi, x is equal to -3. Well, that means it's going to be over here, isn't it? The particle's going to be over here. So in actual fact, you want to work it out. Let's have a look at something else. At t is equal to 3 pi on 2, it's going to be exactly the same. X is equal to 3 over cos of 3 pi on 2. That's undefined. But of course, this here is not including of those points. Why don't we just check the y's as well? Let's check the y's as well. At t is equal to pi on 2, y, which is equal to 4 tan t, 4 tan of pi on 2. What's tan of pi on 2? Undefined, yeah. But let's sort of say at t is equal to, and the same thing as set tan of 3 pi on 2, it would be undefined. So why don't we do at t equals pi? What are we going to have? Y is equal to 4 tan of pi. Isn't that 0? Aha. So what we're saying is we've established this is a particle. And a particle is at various times. What we've just shown you is in actual fact at t equals pi, somewhere halfway in between, then what we've got is we've got x is equal to -3 and y is equal to 0. So at time equals pi, it's there. So how could it possibly be the right branch of this hyperbola? So in other words, when sketching this particle, okay, and sketching this particle, what we need to do, and of course it's approaching infinity, so it's basically the left branch rather than being the whole hyperbola itself. That's a pretty tricky part to it. It's the left branch only. And of course, if you were sketching this, of course, you would have to work out the coordinates of the hyperbola. Isn't that y is equal to, there's no k, isn't it plus or minus b on a, which is 4 over 3x. Okay, so in other words, what's that? Yeah. Yeah, pretty close, yeah. But obviously a lot of the time, yeah. So that sketch you would need to do, this would be y is equal to 4 on 3x. This would be y is equal to -4 on 3x. And of course, the turning point would also happen to be that -3, 0. And of course, it's one of those ones where it actually, as time goes from pi on 2 to 3 pi on 2, it's approaching, or is undefined, which means it's approaching an asymptote. Okay? So that's really as hard as it gets. Okay? Now, I'm mindful of the time here. Let's go through this one. I did say I would go through a bit of a trickier one. This is from an exam 2 question. Now, what I'm going to do is, I want you to, first of all, I'm going to pause the video. I want you to remember, the x component, this is a vector calculus question, the x component is the I. The j component is the j. And my hint to you is, what do you notice about 2t on 3 compared to t on 3? What do you notice about them? About the angles. This is double the angle of this. So the relationship you'll need to use is the double angle formula. See, there's a lot of things to realise just to get the first couple of questions out. Now, what I want you to do is, first of all, it says you need to show that the relationship is this. Y squared is equal to this. And the second thing is you need to find the Cartesian equation. Cartesian means we need y's and x's. And then the last part is to sketch it. But for the time being, I want you to take your time. I'm going to pause this video. I'm going to go through it in a second. Okay, and so just quickly, for some of you that are stuck, what we need to do is we need to label what x and y is. X is equal to sine of t on 3, not I. That's the x component. Y is equal to a half sine of 2t on 3. That's the first thing you need to do. The second thing is, though, I did say this, is that we on the formula sheet, the double angle formulas represent 2x and x. But of course, it could be anything. 2t on 3 is double that of t on 3. So what I'm going to do is I'm going to do this. I'm going to say that sine of 2t on 3 is equal to 2 sine of t on 3 cos t on 3. That's straight off the formula sheet, but I've replaced 2x with 2t on 3. And I've replaced x with t on 3. So therefore what we can say is that over here we've got a half sine of 2t on 3. So therefore a half sine of 2t on 3 is, well, that conveniently is going to be sine of t on 3 cos t on 3. Okay? Now, the question is, how do we get this sine squared cos squared business here? So what we can say is, therefore, y squared is equal to sine t on 3 cos t on 3 squared, which is equal to sine squared t on 3 cos squared t on 3 as required. So in order to do this, you needed to show some evidence of rearranging double angle formula. Now it says, hence find the Cartesian equations. Now think about it. Let's have a look at here. What's x? This is x, isn't it? So therefore what we can say is, that y squared is equal to x squared. Now, what's the relationship? Now I'm going to call cos squared t on 3. I'm going to change that to 1 minus sine squared t on 3. Why have I done that, David? Yes, because from there, it's really easy. That becomes x squared 1 minus x squared. Can you see there that sine t on 3 is x? So sine squared t on 3 is x squared. So therefore, that is our Cartesian equation. X squared outside of 1 minus x squared. Which is actually, it's not a quadratic, it's a, what is it? Why don't we expand it out? It is a quartic, but it's a polynomial of degree 4 though, isn't it? Yes. Okay, now, of course, you'll be asking yourself, well, how do I sketch that? The question is though, when we're sketching the Cartesian, it's not y squared, we're sketching y. So what we're going to do is, now I could I could do it. Let's do a little bit of algebra first. If y squared is equal to, I'm going to leave this like this, x squared 1 minus x squared, then therefore we can say that y is equal to plus minus the square root of x squared 1 minus x squared. Now, you can't really put it in the calculator like that, so I'm going to show you what it looks like. But what I'm going to do is, first of all, I'm going to realise that when we're sketching, we've got to consider the positive, we've got to consider the negative. So we're going to have in the first and the second quadrant, we're going to have in the third and the fourth quadrant. So let's go and do that now. You can't do this without a calculator, but this is at the top end of the understanding of a Cartesian equation. This is as hard as it gets, let me promise you. Okay, so what we're going to do is I'm going to do this, but instead I'm going to go to the new graph and I'm going to go over here, not there, here. Okay, so what we're going to do is I'm going to just show you this, and we're going to go, we're sketching x squared bracket 1 minus x squared, and if I sketch that, it actually is, if I maybe zoom in a bit, whew, let's zoom out a bit. Okay, it's actually sort of hard to see, but can you see that that looks like half an infinity symbol? Because what I'm going to do is I'm going to press tab. And when I press tab, that keeps that there. So what I'm going to do is I'm going to go control, what have I done here? Tab. Okay, let's put a negative out the front. We've just done the positive part. Let's put a negative out the front. Now, so which means we have to use this negative down here. And then let's do the square root of x squared over or outside 1 minus x squared and woolly whooshka. Let's go to, you know what? What's this? I reckon it's going from, is it going from like 0 to 1 and 1 to 0? Let's go to Windows Zoom and let's change the settings. Let's go x minimum to -2 and x maximum to 2. And let's go y minimum to -2 and y maximum to 2. And I think that we might have a bit better time with this. There we go. Now let's just get this little thing. This is giving me the irrits. Oh, it's really hard to do. It's going to be easy for you guys to do. I can't do it with this stupid pen. But as you can see, it is a infinity symbol. Isn't that cool? So what, now you've got to understand what is the domain. You check each point, you can check the x and you can check the y. Sine of t for the particular domain goes from, so the x is only going to 1 and they go from -1 to 1. The y's, they to me look like they don't go as high. They go, that's different. Okay, but you can check the domain. You can check the endpoints of the y's to give you a domain. But as you can see, by sketching the calculator, that's what we've got. And of course, you've got to be very precise. I think this part's easy because we know that we go to 1, but a lot of students, you can see there that that's 0.2, 0.4, that's 0.6. I'd say that's 0.5. So when you're sketching this, if you sketch it and you go all the way to 0.7, you'd lose a mark. Okay, it's very precise. Okay, how are we feeling about all of this? Because, as you can see, let's sketch this. We go from 1, we go from -1. We said it was around about roughly 0.5. You've got to be more precise than me, ladies and gentlemen. Sort of went something like this. I hope you get the mark for that. Do a much better job than me, please. Okay? You would get the marks for that, but it would not great. Are there any questions about what we've been through? Because that is as hard And I reckon that's probably the extent of what you need to know for Cartesian and parametric equations. That's at the hardest end, what we've just done then. Just note though, a lot of the time, you will not have the luxury, the resort of your calculator. Okay? And to my Chinese friends who are not here today, you can watch this on video, please. All right. So I'm going to stop there.